Okay, welcome back for the last day of oceanography, if I understand correctly the program. And I hope you couldn't sleep the last couple of days trying to think how you get waters back to the surface of the ocean, since that's how we left it. And we're going, yeah, and so that's what we're going to try to do today. Try to essentially um, go back to the arguments of Monk and Stommel in view of the new observations of turbulent diffusion in the ocean or gravity wave breaking and the vertical profile uh, that has been observed, and see how that might force us to revisit a lot of those classical arguments. And we are sticking again to the abyss, and what I mean, just so that we remind ourselves what is the task at hand here. This is again a picture of the overturning in the Atlantic and in the Indo-Pacific. Now you've seen that enough times that you probably can recognize it. This is as a function of density. You have to add 1,000 kilogram per meter cube to these numbers. And this is latitude, the Nordic Sea in the North Atlantic. This is what we call the deep cell. It's mostly about topography. It is quite adiabatic. This is what Paula was talking about today. Said what we're going to describe is this circulation of waters that instead enter from the Southern Ocean into the Atlantic and come back at a slightly lighter density surface. This range is more than 1,000 meters. It's very compressed in density space, but in real space it's still a large fraction of the water column. Or if you look at the Indo-Pacific, it's this whole overturning circulation. We want to see how is it that that water comes up. If you do this seasonally average picture, we definitely see water coming up in the net. What we want to understand is what allows it to come back to the surface. So these are the typical height of sea mountains and abyssal hills. The gray one is in the Indian Ocean and the darker one are in the Pacific. And you can even look at things if you really want to push the argument. You remember that we've been told that the overturning in the Pacific doesn't probably penetrate much further than 24 degrees north or a bit further up. And you see that it's where topography essentially disappeared. There aren't many topographic features up here. So there is a strong connection between where you get a strong overturning and when there are topographic features that supposedly help in the generation of the waves that break and drive that circulation. So going back to what we described in the first lecture, I think it's fair to say that the key ingredients in the recipe, and I call it a recipe because Walter Munk titled his paper Abyssal Recipes, but the key ingredients in the theory that had been developed had a number of assumptions that clearly were done to simplify the problem. It's not that anybody strictly believed them, but the question is, in some cases, to see whether some of those assumptions were a bit too simple and in a sense impacted the solution to an extent that they made it not particularly relevant. One was that the ocean bottom is flat. You remember in Stommel's argument, he wants to have this upwelling and assumes that the vertical velocity of the ocean bottom is zero because it has a flat bottom. So that is built in their theory. We know that the ocean, well, we'll come back to that. And the other assumption was that both the upwelling and the turbulent diffusivity are uniform throughout the ocean. So you remember that Walter Munk tried to estimate the upwelling based on an advection diffusion balance in the vertical, a one-dimensional advection diffusion balance, and assumed that both W and kappa were constant. By assuming that both were constant, he had some estimate for W itself. He could measure the stratification, and from this equation he could infer what was the turbulent diffusivity. This should have a kappa T. That was 10 to the minus 4 meters squared per second. That was the argument. There is uniform upwelling balanced by uniform diffusion across the oceans. Stommel's argument instead brought the other piece of the picture, which was the horizontal circulation, and said by just using the vorticity equation in planetary geostrophy, said that there had to be a meridional flow balanced by stretching of water columns, and this dW dz had to be positive because the W is zero at the bottom and it's larger at some depth above it. It has to be positive at some depth above it because it has to balance the sinking high latitudes. Well, then this term is positive, which means that you have a poleward flow in the ocean interior that has to be returned south or along a western boundary current, so you get the cyclonic gyre circulation. So these were the two fundamental assumptions. Now we'll see that essentially all three of these assumptions seem to fail in various ways when you start looking at what the ocean truly looks like. And we'll start with the first assumption that the ocean bottom is flat. It's actually interesting that Stommel's paper are in the end of 50s, beginning of 60s. And it took, I think, 30 years for oceanographers to realize that maybe the theoretical oceanographer to realize the ocean wasn't quite flat. Because all of a sudden, in a few years, Trevor McDougall and in particular Peter Ryan start revisiting the argument that of what happens if you start assuming that the ocean is not really flat. He's doing this experiment again in a lab. Even though Peter Rines was also running numerical simulation, this looks like when it comes to the abyssal problem, people really like to go back to the lab and do some of this experiment. So he's comparing the overturning circulation that he can generate with sinking and upwelling in a flat bottom tank versus a tank that has sloping lateral boundaries. And he makes a pretty simple statement. It's hard to argue against. So this one is again the equivalent of Stommel world. You have a sinking plume along this boundary that has to upwell and drives a poleward flow along this direction. North is in that direction here, and then you have a return boundary current, you have this cyclonic flow. So that's just a repetition of what we've seen. But now he says, let me think a second if I have a sloping boundary and now I have a plume that comes all the way to the ocean bottom and from there all the water rises. Well, if it rises W times A, even if I assume that W is uniform, yeah.
So is there a beta plane or topography? If
yes.
In the okay.
There is a topographic beta plane probably in his mind, or in this particular case he's just drawing it, so probably there is just in his mind a beta plane. He does both the beta plane problem and the F plane problem. I'm sticking to the beta plane because we talked about the beta plane. But the fundamental argument remains in both cases. But here, yes, I think in the lab he would have a topographic beta plane, meaning that there is a change of rotation within the tank, in a sense. So now, if the water is upwelling uniformly, he's making the case that, first of all, W times A, where A is the area at every depth of this tank, W times A has to balance S naught because all the water is coming from the bottom, and then he's assuming that it keeps upwelling as you move upward, right? You don't even need to solve this equation. You already realize that then what must happen if W is uniform as you move two sections that are wider and wider, if this has to be a constant because we balance the overall sinking, well, as you move upward where A is larger, W must become smaller. So it's actually decreasing with height instead of increasing with height as in Stommel argument. You can prove it a bit more formally if you want. You take the ddz derivative of this equation. Since S naught doesn't depend on Z, it's just that source at the ocean bottom, you get the ddz of W is equal to minus W ddz of A over A. So this is just the derivative of this set equal to 0. Now we know what W is. W is S naught over A. So I plug it back in here, and so I get minus S naught ddz of A over A squared. So that tells me, if you remember beta V, the stretching, the poleward motion as estimated from the vorticity equation is proportional to f dw dz. And Stommel insisted that was a positive term. That's why he got the cyclonic circulation. But now, in this particular system, you see dw dz is equal to minus S naught is a positive term, is the source. A squared is positive because it's a quadratic quantity. dz dA is positive if you are in a ball whose area is increasing towards the surface. So this term has to be negative definite, which means that your beta V is equal to a negative definite quantity. So now the flow, instead of being poleward, is equatorward. And the boundary current will return the flow northward along that western boundary, so you get an anticyclonic circulation. So you're saying the fundamental prediction of Stommel is already broken if you allow the topography of the ocean not to be constant. And it's very hard to claim that this is a better representation of the ocean than this one. Both of them are clearly idealization, but the fact that topography is not flat is already forcing a rethinking about the fundamental theory of which way the interior flow should go. Remember that there was no prediction, or well, there was a prediction for the direction of the interior flow, but those flows are so weak that they were not directly measured. So it would be even hard to claim that this particular form of circulation is inconsistent with data compared to that, because both of them predict a western boundary current. That's the only thing you really observed. And the direction of the western boundary current, to a large extent, is dictated only by where you have sources of water, because you have to take the water away from those sources. So just slightly variations in the magnitude of the boundary current would appear. So you're already at the point that the first assumption of a flat ocean probably is not particularly good, because the solution will depend on the shape of the topography. What about the second one that we said uniform diapicnal diffusivity. This was the argument that Munk did. In the absence of any observation, indeed, that's what you do. You couldn't make one up. But now we've seen that, so if we go back to Munk's argument, was that vertical vection is balanced by downward diffusion. You remember that the downward diffusion of the diffusive flux, W prime B prime, can be written as kappa T BZ. Or if you want the W prime B prime, which is kappa T BZ, is also equal to gamma epsilon, right? That's how it is measured in the ocean. You remember that was Osborn formula that related the buoyancy flux to the dissipation of turbulent kinetic energy. It's what we wrote last time. And you've seen a second why I decided to think in those terms. The Wt is equal to both minus kappa B bar Z. This is the diffusive closure, but when you measure it, it's actually equal to some mixing coefficient times the turbulent kinetic energy. The reason I'm mentioning it is that now I'm showing you as a function of depth a profile of epsilon. This is something I didn't get to show last time, but it's the third experiment that I would have been talking about had we gone forward. You remember that we showed an experiment that looked at profile of kappa and epsilon in the North Atlantic, in a region where the topography was very smooth. In that case, epsilon was decreasing towards the bottom. But now when we went in the Brazil basin, epsilon was clearly increasing towards the bottom. This is another experiment similar to the one in the Brazil basin, now in Drake Passage. It's another place where topography is extremely rough towards the ocean bottom. And you see your gamma that starts at value close to 10 to the minus 9 in the upper part of the water column. This time the vertical axis is height above the bottom. People start using at this point in the literature height above the bottom as a coordinate, because they tend to see that the mixing is always enhanced close to the bottom topography, so it's a better way to average than in absolute height. So as a function of height above the bottom, you see that the epsilon is increasing by an order of magnitude by the time you get close to the ocean bottom. And it's in the bottom 500 meters to 1,000 meters where the values are really strongly enhanced, right? But if gamma epsilon is increasing towards the bottom, or if you start from the bottom and go up, means that gamma epsilon is decreasing with height, so this term is negative. Right? So now we have the second problem, which is a repetition of the conundrum that I was bringing up at the end of last lecture. That Walter Munk wanted to use this balance to estimate the upwelling of waters through the water column, and now we've seen because of the profile of epsilon, it looks like actually we are driving sinking of waters. Waters are getting denser. To understand a bit more where the disagreement with Munk's argument comes about, is that we could rewrite our turbulent diffusivity expression, right? The dz of kappa tbz. We use the down gradient diffusive closure that you've seen a number of times. Unlike in the problem that Bill was talking about yesterday, in this case, it's actually pretty defensible. You do tend to see that gravity waves, when they break, they tend to mix stratification. You don't have many examples when they manage to unmix stratification. There aren't additional constraints that make it happen, like in the two-dimensional turbulence problem that Bill was talking about. So now, if we write it in this form, just to understand, since Walter Munk was talking in terms of turbulent diffusivity, where is it that his argument seems to have gone wrong compared to observation, is that I have to take the derivative of kappa t times bz, the vertical derivative. I can take the derivative of the product is ddz of kappa t times b plus kappa t times the double derivative of bz, right? What Walter Munk was assuming was this term is small, because he assumed that kappa t was essentially uniform, and so he was claiming, well, kappa t is clearly a positive definite term, and the bzz is positive because typically the stratification in the ocean is weak in the abyss and become much stronger towards the surface. We've seen now pictures over and over from data. Paola has shown a number of them from more idealized model. You see that the abyssal ocean is weakly stratified as you move towards the surface, strongly stratified. So clearly this term itself was positive. However, now this is a profile of epsilon. So you remember that if I use this expression, gamma epsilon is equal to kappa t bz, so I can infer kappa t from this relationship, because kappa t is just gamma epsilon over b bar z. So I can show kappa t here. You see that the turbulent diffusivity itself is increasing even faster than epsilon towards the ocean bottom, mostly because kappa t is proportional to epsilon, which is increasing towards the ocean bottom, and inversely proportional to bz, which is becoming weaker towards the ocean bottom. So you get a very rapid increase towards the ocean bottom of your turbulent diffusivity, and therefore it turns out that this term, it's a negative term, and it's much larger than this other term. So this dominates or sets the sign. At least observation suggests that this sets the sign of the vertical profile, and that's why you get a negative overall term that implies a sinking of water, right? So now it seems that all the fundamental assumptions that we built our theory on are falling apart, so we have to try to go back and see what we can save and what we can understand. The first and most important issue being that we still believe that there is sinking and convection at high latitude that is being measured. That water has to come up somewhere. We can't just claim that it's sinking and seeping through the solid earth. And so you realize that there is a simple answer to that problem, at least at a qualitative level. This is repeating the part of the picture I showed you last time. I didn't show you this part. This is what you probably have all figured out during the night. If I have a particle sitting in the stratified ocean interior where the turbulent diffusivity is increasing toward the ocean bottom, indeed this water parcel is mostly mixed with water below it, but it's not mixed with water above it, so as a result of mixing, it's getting denser and sinking. But now think about a water parcel sitting right over the topography. Well, then this water is not being mixed with topography. Turbulence doesn't mix through hard rocks, so this water parcel is only mixed with water above it. So along the boundary, waters can turn into lighter waters. If they turn into lighter waters, it means that they can slide along topography and come back to the surface. Or another way to say it is that I kept insisting I cannot erase anything. Here, yes. Okay. I had to be careful about. Okay. Well erased. So if I plot my W prime B prime as a function of height, you remember W prime B prime is negative in a stratified ocean. What I'm saying is that it's increasing towards the ocean bottom, it's becoming more negative. But then we also know that there is a boundary condition, no flux through the boundary, so that flux has to go back to zero. Right? So you have that dz of W prime B prime is now. I'm going to confuse everybody if I do this. Maybe let's call it the kappa T B bar Z. This is negative here, right? While all of a sudden the ddz of kappa tbz, however, has to become positive right at the bottom of the ocean where the flux has to go back to zero. So if you think about what is happening here, I keep insisting this term is negative in the water column, and that's true all the way up to close to the bottom boundary, but then it has to go to zero because there is a no flux boundary condition right at the solid boundary. So this is equivalently a cooling of the water column, if you think about it, right? This is your advection, this is the diffusion. If it's negative, it means that you're cooling water, and that's why they're sinking. And then there must be a boundary layer at the ocean bottom where instead you have effective warming because the buoyancy flux from divergent becomes convergent. Yeah?
Why is there no observation, for instance, in those wells? Because it is indirect, or?
Very good. I was coming to that. So you remember that the argument we use to estimate our buoyancy flux relies on a statement that if I measure the turbulent kinetic energy, I can infer the buoyancy flux, because when I mix a stratified fluid, some of the work I do on mixing the momentum or reducing the shear goes also in raising water, so creating potential energy. Bottom boundary layers tend to be weakly stratified. Think about the limit of no stratification, just for simplicity. Right now, if there was no stratification, I can still have a very large epsilon. Turbulent kinetic energy still gets dissipated if we believe in the zeroth law of turbulence that we are not so confident about anymore. But the idea is always turbulence will tend to push energy down to smaller scale where it gets dissipated. But if there is no stratification, you don't generate any potential energy. So that gamma is essentially zero because you have a lot of epsilon, no flux. So this approach to measure turbulence will work very close to the boundary, but not in the boundaries. So you can't even use it. Then in practice, here they write zero, but the first point that they actually have in this profile is generally at least 100 meters above the bottom. That I was talking with somebody over breakfast, It has an important historical context. The people that were using these profilers to measure turbulence through the water column during the Brazil Basin, that's the first time they really went to measure the profile all the way to the bottom of the ocean, early on realized that it would be interesting to see something close to the boundaries, even though those arguments don't hold. At least you could measure what happens in the boundary layer itself. And the first profile they took, they managed to hit the bottom and they nearly lost the instrument. The HRP is a $1 million instrument. There was only one. They had to wait a few days until it decided to pop back up, and they recovered it. And since then, they never gone within more than 100 meters of the bottom, less than 100 meters of the bottom. So there is a practical component. So they generally don't go in the boundary layer. Even if they did, it's not clear what they could do with this kind of data. Yeah.
According to that picture, water sinks in the first part and rises and then gets stuck at the middle.
Well, we'll see in a second. It's a good question. If you think about vertical walls, you have a problem. But as soon as you start thinking about lateral walls, water can rise along the boundary continuously because there it's always being warmed. So it's not going to go vertical. So you have water sinking essentially vertically. So now I'm drawing density surfaces which are nearly flat in the interior. They have to bend close to the boundary because you have a boundary condition on no flux. So now the normal to the isopycnal direction is along the boundary, so that's how it works. So it can work. Whether it does, it's still an open question. So now the argument would be, well, maybe we have a lot of sinking in the ocean interior and upwelling along the boundaries, and that's how we have to think about the problem. And we have to give up on these ideas of vortex stretching that Tome was talking about, because we have a variable topography in this picture. So the first thing I want to show you is, first we can, or at least maybe let me say exactly how we're going to do this so that everybody is somewhat pleased or displeased, but you see that there are a number of steps. The first thing I want to show you is a few numerical simulations of the kind of what Paula was showing yesterday, where you use this idealized version of a global ocean model to see how circulation of the kind I described do actually arise. So it's not that I particularly believe the numerical simulation, but it's a good way to get started and start seeing how the circulation arises and how much it changes the picture that Stommel and Mank put forward. So you start understanding that this distinction of upwelling and sinking that I'm describing here really changes quite dramatically the circulation you have. Then we'll try to make contact between this numerical simulation and the real ocean by trying to use scaling laws to reconstruct buoyancy flux in the real ocean and see whether, at least at the order of magnitude level, what we're describing is sensible and consistent with what we expect to observe in the real ocean. And then we come back and we try to set a reduced model with reduced dynamics that we can actually analyze and start understanding. So we start complex and we go simpler and simpler. We move to the end. So by the end, we think that we can understand a bit more the fundamental theory. But the reason I do it this way is that first, I find that people need to be convinced that this kind of arguments actually do hold in a fluid that has a turbulent buoyancy flux profile of the kind of what I described, and that it really impacts quite directly a leading order the circulation you get.
Why do you question the validity of a numerical experiment? It's a discrepancy between the hypotheses you will make for doing a numerical experiment and what the real ocean is, or is it something else?
I don't think, well, you'll see that the experiment I run will make some choices that quite a few people, I hope, will object to. But no, it's not that I don't believe the numerical experiment, and I want to understand it. And it's not that easy to understand that numerical experiment because it's too complex. So eventually I want to reduce the dynamics so that I can understand the fundamental dynamics at work. So the experiment, this is what I guess Henry Stommel would have done in the lab, just to make sure that this basic idea is something you observe. And it will make some interesting prediction, I hope. You'll agree that they are quite counterintuitive. So again, when you see that, you'd like to understand from first principle why that happens, not just observe that it does happen. The simulation I'm going to run, I guess in that sense, is non-Paula-like in the sense I want to have a simulation that is appropriate for the Pacific. I don't want to have convection at high latitudes in my simulation, because you've seen mostly that the best example of an overturning that span a large fraction of the water column, and it's all diabatic, is in the Pacific. So we want a simulation of the Pacific as a toy model to test some of these ideas. So this is topography of the Pacific. You have a big basin here and a reentrant channel, the ACC, to the south. So we are going to idealize our numerical simulation as a channel with a reentrant flow to the south. And what we'd like our model to do is to be able to reproduce three aspects of the circulation. Well, the first one is that the ocean is stably stratified. If we get a simulation that gives us an unstratified ocean, that's not a good description of the real ocean. The second thing is that we'd like to see an ocean that has an overturning circulation of this kind, where there is water coming from sinking in Antarctica. There is convection around Antarctica. Water sinks into our basin. It's diffused upward and returned back at a lighter density surface. So that's the second criterion we want. And the third one that we'd really like to have is that we want our buoyancy flux to increase towards the ocean bottom. That's the other part of the observation that seems pretty compelling, and I will argue that none of the simulation we've seen this week and none of the simulation you typically see, idealized simulation that you see published in JPO, reproduce that aspect of the overturning circulation. And the question, of course, does it matter?
So this aspect you are talking about, so is it localized in the ocean, or
okay, that's a good question. It turns out that this profile has been observed every time you take a vertical profile over rough topography. But it's not if you go on very smooth topography. However, where you have smooth topography, the buoyancy fluxes are very weak anyhow. So when you take a global average, this is the pattern that you get, because it's dominated by places where you have a rough topography. So the average profile has a shape like that. Now, that said, it's very heterogeneous. So now this is the setup we're going to use for our numerical simulation. This is run with the MIT General Circulation Model, but it's very similar in terms of configuration to the simulation that Paula has shown you, except that the first thing you see is I'm using a basin here. This is the topography only, and you see that it's a bowl-shaped basin or a bathtub. Unlike the simulation Paula was showing, they always have vertical walls, because I contend that makes a substantial difference. We are going to look at a simulation with vertical walls. So as I describe this simulation, you should all try to think and anticipate what happens if I put vertical wall in this simulation. And I made some statements about what people would guess, because I asked many people to try to guess what happens with vertical walls. And they mostly, well, a good fraction doesn't get it right. Then I stated that in JPO, the reviewer got very upset that I wasn't fair to the community by making statements about what people guess or don't guess.
Is the slope realistic? I mean, it seems very gentle, I thought.
It's not.
Right. So isn't vertical more realistic than that?
I'll contend that it's fundamentally different. And we're going
to... It's a continuous process, and it depends on the slope. Right?
Well, I would contend that the vertical wall is a singular limit of this problem, of this solution. It really starts, well, where vertical is vertical enough to allow non-hydrostatic process to develop. That's generally what happens when you go really vertical. You have steep enough slope, and the slopes along mid-Atlantic ridges and seamounts are weak enough that that's not the issue. I mean, you have to remember that the real ocean has aspect ratio are incredibly small, so those slopes are always very small. Now, these are even smaller, just to keep it simple. I mean, we've done kind of a whole series of examples where we change the slope. It doesn't change as much. Here, you resolve the numerics much better. You have a smoother slope. But we'll get to that, because we're going to get to do estimates where we use the ocean, the realistic ocean topography, to see to what extent with the realistic topography you might change that story. So we'll get to that.
I also have a question. What sets the width or the height of the boundary layer? Is there a theory on that, or do you just take something from which corresponds to observations?
So that's a good question. I don't know whether you're asking from fundamental theory or in the numerical model.
Good question. I didn't think about that. Well, what do you get from the theory?
So from theory, I would contend that we don't know that much, because you're talking about boundary layers that develop over rough topography. So one of the scales that clearly enters is the roughness of the topography. In the atmosphere, that's generally considered an important scale. However, you also generate hydraulic jumps, bores, then you generate nonlinear waves all on that boundary. So and there are very few observations of the boundary themselves. So the folklore, and I have to call it folklore because there are very few references that stick their neck out and try to give you numbers, that it's anywhere between 10 and 100 meters, depending on where you go. And it doesn't scale with the strength of the turbulence as far as they can tell. Sometimes they have very high turbulence rates and very thin boundary layer, so it probably also depends on the background stratification you're acting on. In the numerical model, okay, so this is our numerical model. So there is this basin, which is a bowl, and there is a re-entrant channel to the south, so there are periodic boundary conditions here. We are blowing a wind over the Southern Ocean because you remember that Paula reminded us that it's essential to drive the system to put a wind along the southern channel, because it will set the stratification in the ACC, which then gets communicated to the rest of the basin. We're going to impose some heat loss. We are restoring to a very cold temperature over the channel, so you're going to have convection here while we restore to a uniform temperature over the basin, which is pretty warm, so you don't get any convection anywhere else. That's just how we set it up. And now the part that you should really have some problems with, but I'll explain why I want to do it this way. We're going to prescribe the buoyancy flux. So I'm not going to prescribe kappa T BZ, where I just prescribe a kappa T, but I'm just going to prescribe gamma epsilon. And the reason I do that is that I want to prescribe a gamma epsilon that is increasing towards the ocean bottom as a function of height above the bottom, and then it goes back to zero on a boundary layer, which I think has a thickness of, I think 60 meters. It's 2 grid points. I prescribe the buoyancy flux, not because I believe, the difference between these two forms from a numerical perspective is this one would respond to change in stratification. Your buoyancy flux has a kappa T, and then if it's weakly stratified, the flux is weak. If it's strongly stratified, it has a strong flux. Instead, here I prescribe the value. The reason why I do that is that I want to say, let me make the hypothesis that I know what is the profile of the buoyancy flux. I prescribe it in this model, so I solve a buoyancy equation, dB dt, that we'll have on the right-hand side ddz of gamma epsilon prescribed. And I want to know if I have a buoyancy budget with a turbulent profile of that form that I'll contend that most ocean models generally don't get. Can I get, as a response, an ocean which is stably stratified and with an overturning which is consistent with observation? So that's the question I'm really asking. I say, if I know that part of the solution, do I get the other two parts to be consistent? And do I need sloping topography in order for the stratification?
I have a question.
Oh, sorry.
So how can you prescribe the flux inside everywhere and the buoyancy at the surface at the same time?
Well, the buoyancy, technically at the surface, this buoyancy flux goes to zero. I have a separate condition, so there is an addition to the flux due to the boundary condition at the surface.
No,
So there is an additional flux right at the surface. This is not the full flux, that's true.
oh, so you modify the flux at the surface,
at the surface it's modified.
to become a relaxation.
Yes.
Oh, okay, got it. Thank you.
Which makes a difference, but just at the surface. But it's a very good point, yes. At the bottom, instead, it goes to zero, so it's satisfied at a normal flux, so I don't have to add anything on top.
So one more question. So you're prescribing the buoyancy flux, but you're also solving for buoyancy and W velocity and so on, right?
Yes.
So there's another W prime that comes up and a B prime.
Well, but that's resolved.
Yes. So what do you do with that?
So the main difference that maybe what I didn't tell you is what is the resolution of this model. I think it's 1 degree in the horizontal.
So it's very
pretty coarse. So the W prime and B prime are balanced motion, so they're not going to affect a diapicnal flux.
Okay.
So yes, this is a model in the spirit of the coarse models that Paula was talking about, where I don't even resolve geostrophic eddies. Those are parameterized with a gentle Macquillian parametrization. But all of these issues for this particular solution are not terribly relevant. Instead, what you might expect is that when I start running my simulation, I have winds that drive an Ekman flow towards the equator. So they try to tilt isopycnal upward. That's how you set your stratification. But then there is barochrinic instability represented by a gentle Macquillian parametrization that tend to relax them. So isopycnal, we get some mean slope in the ACC, and then that stratification gets communicated to the rest of the ocean, and we want to see what solution we get. So the first thing is that we look here. This is depth and latitude, northern hemisphere, southern hemisphere. This is my channel, and this is my closed basin. And the black lines are stratification, so that this ocean is stratified, and that stratification is not unlike that of the real ocean. And I'm also drawing in colors the overturning circulation. You see water is sinking around Antarctica, coming in the interior, rising in the basin, and coming back here. the overturning, even in terms of magnitude, is 15 Sverdrup or so. We've chosen values of buoyancy flux which are realistic. We chose the area of the domain to be pretty close to that of the Indo-Pacific basin, so we're getting an overturning which is consistent with that basin. So up to this point, we contend prescribing that buoyancy flux profile, I got an overturning and stratification which are at least consistent qualitatively, if not quantitatively, with the observation. So the solution is self-consistent. But now we can start looking in terms of what I was describing here of upwelling and downwelling. Oh, this is really bad. This picture here. I'm not sure you can see. On my screen it's much better. I don't know, these lines are continuous. So here we are looking at a few sections across this domain. This is again latitude, this is now longitude and depth, and I'm taking a few sections. I'm showing you the vertical velocity in that domain. I just want to see how waters are moving in the vertical if I look through a section. These lines are density surface. They should be continuous line, because I'm taking a section. I also show you the density surface. But more importantly, what you should look is that you see that there is a lot of blue here, right? Blue is negative velocity. It means the water is actually sinking down there. So indeed, we see that in the stratified interior, where there is stratification, water is going towards the bottom. But then you see, I don't know, can you see that there is a red stripe right along the topography? That's a positive velocity. So it looks like there is water sinking in the interior, and then a stripe of much stronger velocity along the boundary. Turns out that these velocities are a factor of 10 nearly larger than the sinking velocity, so there is a very fast return flow along the boundaries. Right, so that pattern is really realized in this circulation. In some sense, it has to, because I prescribed a buoyancy flux that requires that. Questions? I can repeat the question.
Is those density surfaces coming out of the wall? That's not very ocean-like. They should all come from the surface.
No, here I'm looking at the zonal section. It's really this boundary condition. A density surface on the lateral boundary has to enter a normal flow. So that's what.
It says latitude.
Well, this. Well, unfortunately, the picture, but this is
talking about the
latitude, but this is longitude. Oh, this one up here.
Yes. So what?
So you're worried about these things here.
Yes.
Well, here is that you're mapping from densities to Z. So if you look in density, they actually all come to the surface. When they remap, they look like they hit the boundary. And yes, absolutely. Otherwise, you'd worry seriously.
And is the red upwelling velocities exactly in those grid points that we have, that you prescribe the buoyancy flux to be?
Negative, yes.
It's exactly in only though it doesn't spread away from that.
No. After that, the problem you have when there is no flux here, as we said, the rest of the dynamics is mostly geostrophic, so I can't really cross density surfaces, so I don't provide any diffusion to allow waters to cross the density surface. All this should answer Freddie's question, why do we want to go back to a simpler problem at the end to convince people?
I was wondering, can you give us the order of magnitude of the red vertical velocity and the blue?
I could, but I wouldn't tell you anything. In a sense, you remember that they're all very weak velocities, so maybe the easiest thing to do is, if you remember, it was, 3 meters per year in Stommel estimates. The sinking here is probably a factor of 10 larger than Monk's estimate, because these divergences are pretty large, and the return flow is 2 orders of magnitude larger than Monk's. So it's 30 versus 300 meters per year. So they're much stronger, but they're still very weak velocity you won't directly observe.
Okay, so in the real world ocean, what is the energy source of the upwelling? I mean, the upward buoyancy flux near the bottom.
What is what?
What is the energy source? The source of the energy, like what drives the upwelling?
Well, this is gravity wave breaking that provides that profile, and then it just goes to zero. I don't even worry really what happens there. I just know the buoyancy flux is becoming less efficient. In some sense, what is funny here is that what we generally think about an energy source, I mean, this part of the buoyancy flux is actually driving a sinking of water. Then yes, all the buoyancy is gained along the boundaries, but the buoyancy flux is going to zero there. We can do the energy budget if we want later on. But first we should understand the dynamics, which we are not there yet.
Is this boundary upwelling symmetric on the west boundary or east boundary?
Yes, because I set up a symmetric system, so I don't break any symmetry. But I can break it if I change the slope on one side versus the other, or if I make the buoyancy flux larger on one side versus the other. Well, but not east-west. In this boundary layer, well, we'll get to the theory. Yes, it would if the boundary layer was as thick as the Stommel boundary layer thickness, but they're much thinner, so beta doesn't really affect them. But that's why I think that doing the analytical problem at the end actually helps a lot to understand some of these properties.
I guess I'd just like to make it, is this working? A comment about the boundary upwelling, which is that this phenomenon happens even if you have molecular diffusivity and a sloping boundary. If you have a stably stratified tank with salt and you slope the boundary, then there'll be an upslope flow driven by molecular diffusion for exactly the reasons that Raf is explaining.
We'll get there. We do the solution, then you see that you need any kappa.
Yeah, but the point I'm making is you may think that somehow the boundary upwelling is due to some details of turbulent parameterization or anything like that. But no, it's just a consequence of having no buoyancy flux through the boundary and a slope. And that's it. It happens with molecular diffusion as well.
Yeah. The only difference being that the creeping flow you get with molecular diffusion is tiny. And that's how it was first derived, and then people abandoned it because they thought it was of no consequences. When you put turbulent diffusivity, then the number gets larger. But we'll see solution, which indeed shows you that as long as you have a no flux boundary condition, or you could even put a geothermal boundary condition, you are going to get some upslope flow. I think Tom Peacock, for the people who know it, even conceived of a wedge that has two sloping boundaries, that put in a fluid, it's neutrally buoyant, develop these boundary flows that propel it so it moves slowly through a stratified water column. I'm not sure what the use for that is, but it's a very good demonstration of these dynamics.
It's a device for transporting minuscule payloads over very small distances excruciatingly slowly.
Okay, now we know what it's useful for.
I might have
always turn it off.
I might have missed a point, but what's the size of the upwelling compared to the downwelling?
We'll see why it's a factor of 10. Well, the magnitude of the upwelling versus downwelling, I'm not going to tell you because this is what's coming up and I want to create some suspense. In terms of absolute velocities, I told you that the boundary upwelling is nearly an order of magnitude larger than the downwelling, but I haven't told you the transports yet. And I want to wait a second because it's a very good question. I think this is what makes the whole story quite interesting. So now, if I want to measure the transport in the boundary layer versus the interior, I can actually convince myself that what I'm really asking, I want the transport, meaning the diapicnal flow, the flow across a density surface like drawn here. And this could be a density surface that keeps propagating until I get to another boundary. So if I want to know what is the velocity, now I'm calling E the diapicnal velocity. Technically, you can really do it for the diapicnal velocity. Here we're going to cheat and we assume, at least in the interior, that the diapicnal direction is vertical. So I can compute E, the velocity norma to that density surface, and that is just given by minus the divergence of the buoyancy flux over B bar Z. This is essentially Planck's argument, if you remember, is W B bar Z is equal to minus the divergence of the buoyancy flux. You could do it in a more general form if you want, and you have isopycnal that are not quite vertical. So I can do the integral only on the portion of the isopycnal that is not in the boundary layer, right? Where the buoyancy flux is divergent. Sorry, it's convergent, and so I have sinking, and then I can repeat the same calculation to compute the transport of water along the boundary layer itself. So I can compute how much transport there is in the interior versus how much transport there is in the boundary layer, exactly the question that was asked, right? And all I really need to know to do the calculation at leading order is just the vertical divergence of the buoyancy flux and the stratification, which I have from the numerical solution, and again, consistent, you might expect dz of w prime b prime. You see, dz w prime b prime is negative, so the fact that it goes from a large value to 0, it's actually a positive ddz of w prime b prime. So if this is positive, you get a negative velocity, which tells you that the transport is negative. Along the boundary layer, dz w prime b prime changes sign, and so now you have a transport which is positive. But now I can do it for the simulation over the whole basin. So we're going to compute the diapicnal transport across the density surface on the fraction of the density surface which is within the basin, just to compare the two transports. And this is what we get as a result, and we do it for every density surface. So these are density surfaces. The black one is the sum of the upwelling and the downwelling, right? So it's a black line, and you see that it gets largest at the density of 28.2, and it's close to 10 Sverdrups or a bit more, and then it comes back. Now this is exactly the picture you're seeing there, because I'm taking a zonal average, so I average both what happens in the boundary layer and the interior. If I look at the density surface 28.2, where it has a value close to a bit more than 10 Sverdrups. However, now I can separate the upwelling as well in the boundary layer versus the sinking in the interior, right? So I see that the upwelling in the boundary layer transport in the excess of 35 Sverdrups, and there is a sinking, this is the blue part in the interior, of order of 20 Sverdrups. So 35 minus 20 gives you 15, maybe the value that you see there. Now what this is suggesting is that this overturning is a huge cancellation of much stronger upwelling along the boundary and sinking in the interior. If I take the zonal average, I average them together. This 15 Sverdrup is what balances the sinking at high latitudes. But there is also all this sinking happening in response to mixing the convergent water towards the bottom, and then the boundary layer brings all this water back to the surface, and so it's 15 Sverdrup plus 30 Sverdrup of sinking is balanced by this 15 Sverdrup of upwelling. So this is another sense in which this overturning circulation is just a big residual of much larger terms. Yeah.
This graph is slightly confusing. So if you have 28.2 density surface, I would expect that the boundary layer would be at some higher density surface, but you have a vertical axis with density.
Sorry, I'm not sure I understand the question.
Okay, so the red curves that you measured, the boundary layer transport?
Across the surface 28.2, right? So this could be the density 28.2. So in one case I'm computing the transport here across that density surface. This is the red one. And then I compute the transport across the density surface away from the boundary layer, and that is the blue line. Is it a bit better? Sorry. Is it clear to everybody a bit what that is? So I'm really looking at the transport across this density surface. Again, this is a zonal average, so I'm doing it on the full 3D or a full 2D surface. And the black one is the transport across that whole density surface, so it has to be the same as here. I'm taking a zonal average. Again, I'm summing everything. But now, since I know how to decompose the upwelling just over the fraction of the area that is in the boundary layer versus the fraction that is in the interior, I can compare how much upwelling there is in the boundary layer versus how much sinking there is outside the boundary layer. But we have both this flow on top of it. If you remember, what I mean by outside the boundary layer is this region that's just a few hundred meters above the boundary layer where there is substantial mixing. So both of these flow really are quite confined to the topography. This is just in the boundary layer, and this, which say it's 10 to 100 meters high above the topography, and this is another few hundred meters above where there is sinking. And then once you move away from that, it's essentially adiabatic.
Is it a in situ density or a spatial density?
It's potential density.
All right.
But well, in this particular case, it doesn't really matter, right? Because I think I'm using a linear equation of state. So the density is just proportional to temperature. So I think this is, you can think about it as density because we don't have compressive effects. Yeah.
I'm trying to imagine what would happen when the boundary become a strict flow. Oh.
I'm going to ask you though.
Okay. So the red curve would actually disappear, right? Because there's not enough like vertical crossing of the with the boundary.
or mostly constant stratification is already intersecting the boundary right angles, and you don't really get much of an upslope flow. Yeah, so what do you think happens? Because this is the simulation that Paula was showing yesterday. This is what pretty much all idealized studies of the overturning tend to do. Just to remind you, Paula was only talking about the adiabatic part of the circulation where those fluxes are zero anyhow, so in that case it doesn't matter. But when you start asking what happens below that adiabatic circulation where those fluxes are large, I would contend that yes, they do matter. So what do you think happens if I run the same simulation? And again, I do these funny things where I prescribe the buoyancy flux with all the caveats that come with it, but I insist that I want to know whether if I have a closed box with vertical boundaries and the buoyancy flux profiles that increases towards the ocean bottom, I can expect to have a realistic overturning and a realistic stratification. Because that's, to me, a way of asking, well, the models that are generally being run, well, we'll get to it. First, I want to hear, what do people think? Can you do it? Do you think you get a sensible solution? If you don't, people want to guess what might happen. The atmospheric people should answer. Because you remember that the buoyancy flux I prescribed should be pretty familiar to atmospheric people. Essentially, I'm prescribing warming close to the boundary, because that's where I have a divergent the buoyancy flux, and cooling all the way above it, because now this is becoming like radiative forcing. I'm just prescribing what the thing is. It cannot change. So I'm warming close to the bottom and I'm cooling above, and it looks a lot like the tropics. So what do you expect should happen? I've given you most of the answer. Okay.
So they say popcorn convection.
Yeah, that would require very good resolution, which I don't have. But my two question was more, absolutely, you do. But more importantly, I'm asking, what do you think will happen to the overturning and the stratification? Those are the two things I know about the ocean. Will I get some stratified ocean? Will I get some sensible overturning? Yeah, I heard somebody saying something. Yeah, I probably get an unstratified ocean for the most part, right? Now we can look at it. This is the picture you get. Oceanographers generally, when they're asked this question, they go on to a very contrived argument to make the overturning turn the other way around, which just can't happen because I'm still cooling here. So you get convection here, the water moves up, returns down. So the direction of the overturning is similar to what it is above. It is much more confined to the bottom. But even the magnitude in this case is much larger. But what you see is this density surface become nearly vertical. There is very weak stratification in that part of the water column, mostly because indeed you're warming at the bottom. You're creating convection that keeps the system nearly marginally stable to convection, like in the tropics of the atmosphere. So you don't get a solution that looks anything like the real ocean. If you actually want to know exactly how the water mass conversion happens, they have water sinking down here. Now, along the bottom boundary layer, you can have a diabatic velocity, right? Because that's where you're warming, so the water can move towards lighter density classes by just flowing along the bottom horizontally. So that's what was happening along the boundaries, but since now the boundaries are flat, all that flow doesn't drive any upwelling, it just moves horizontally, right? So it doesn't bring the water back up, it just allows that water to become lighter, and then this water can just rise in the interior long density surface, so it doesn't cross density surface much because there isn't much of a buoyancy flux. If you see, actually in the net, it starts coming back down a bit in the interior. That's because there is some net cooling, so the water rises and sinks a bit through these density surfaces. I think that the details of the solution are not particularly important. It's a funny solution anyhow. But what it's telling you is that every time you see a numerical simulation of the abyssal circulation in a square box, where people do not prescribe the buoyancy fluxes, but they're going to they try to contrive their solution by using a turbulent diffusivity that gives us a stable stratification and an overturning in the right direction, their buoyancy flux is going to decrease toward the ocean bottom instead of increasing as it should. So it's not consistent with a basic feature of the ocean circulation. Because if you insist on doing that, you end up with an ocean which is essentially unstratified, which is not what the real ocean looks like.
So I know you told us to ignore the details, but it looks like the overturning is a lot stronger. Is that correct?
Yeah, and that has to do with the fact that this is where this simulation is a bit funny, because I'm insisting on prescribing buoyancy flux independent of the stratification. in a very weak stratification, my buoyancy flux would actually go down, but the system doesn't know about it, so it can drive a very strong overturning because I still have the same gamma epsilon without the weak stratification, which would dampen the flux.
Okay, so we can't answer the question of how the overturning depends on geometry yet. Because otherwise I would conclude
this is where we go to the more idealized dynamics, and then we can answer those questions. This one, for the moment, is just an hypothesis testing. I wouldn't call it simulation. I mean, they're not realistic in the sense I prescribe the flux. I just wanted to see the new element that we're really imposing on what is generally the classical theory is the shape of that buoyancy flux, and I want to see how does that affect the solution. But then in practice, it is true that that buoyancy flux depends on that stratification. That feedback is important. So if I want to do the full problem, I have to ask that. If I just do half of the problem, then I get funny circulations. It works much better with the sloping boundary because I would contend in that case, I'm using a realistic buoyancy flux profile in a context where that buoyancy flux profile does the work of the real ocean. So everything falls a bit into place. If you go back one way to understand it, if you go back here, you can still estimate a turbulent diffusivity, right? Kappa T should be equal to the buoyancy flux divided by the gradient. The turbulent diffusivity that I got in the simulation with sloping boundaries, since I prescribed the buoyancy flux and the BZ was realistic, is a kappa T of order 10 to the minus 4 meters squared per second, which is sensible. In this simulation you've just seen, your kappa T is more than an order of magnitude larger, so it's a huge turbulent diffusivity, and that's why you get a very strong overturning, but it's because I fixed that term there, which in the real world I wouldn't.
So do you think that imposing an average for DZ kappa T BZ bar, or to impose it homogeneously rather than very localized in the ocean may make a difference?
So there are two things. We don't impose it homogeneously, right? Because it's a buoyancy flux which has a similar form as a function of height above the bottom. So horizontally we'll have a lot of variations no matter what, because the profile in a sloping boundary makes it vary, and unfortunately we didn't have the last part of the lecture 2 where we showed the example if you do that whether you recover circulation in the ocean. The answer is yes. So the fact that it's intermittent will tend to focus the upwelling in certain parts of the ocean versus others, but the overall bulk response is still similar. But I think I'll be able to convince you a bit more once we do the analytical problem, which shows a bit the dynamics, if we ever get there. So now, very quickly, so here I want to let you ask many questions. I mean, you can ask as many questions as you want as usual, but I don't think it's worth spending too much time because I'm not giving you any detail. The only question I wanted to answer or give you some hint for is whether that cancellation between upwelling and downwelling is something you should expect in the real ocean. And how do we go about that? And the real ocean, the big issues were, indeed, there is a lot of heterogeneity in the buoyancy fluxes. They are not the same everywhere. There are very large variation in slopes. They are much more confined to the lateral boundaries. Is that enough to change the overall picture? And the way we've done it in work that here with Nikurashin, with a former student, Max Nikurashin, was to move along a few steps, and this is really qualitative. I'm not even sure it's qualitative, but a hand-wavy argument to get a sense of at least what are the order of magnitudes of these terms. So what we've done first, we relied on work that, so if you want to know what is the buoyancy flux, we need to know the DDZ of W prime B prime, right? We remember that what drives that diapiconal circulation is the DDZ of the buoyancy flux. So how can we get the buoyancy flux? Well, we said that according to Osborne-Cox, we can get the buoyancy flux if we know epsilon, the dissipation of kinetic energy. How do we get the dissipation of kinetic energy? Well, if it is all coming from gravity waves breaking, we need to know what is the rate of generation of gravity waves and what fraction of those waves end up generating mixing. So the way this calculation went is that first we computed the rate of generation, the work done in generating gravity waves in the ocean. And that requires two steps. You can look at the generation of internal tides. That's the problem that Bill described or alluded to. He didn't go into much detail either. In order to do that calculation, what you really need is to know the velocity, the barotropic tidal velocity. You need to know the main topographic features in the ocean. Those are the ones that excite the displace density surfaces and generate internal waves. And then you need to know something about the bottom stratification, which you get from hydrography, meaning vertical profiles that have been collected everywhere in the ocean. So you have the three elements, you just use linear theory, and you can get the rate at which waves are radiating the ocean interior. And I think this calculation is done by Nykander based on the formula that was derived by Bill. And the number you see there is also something I think Bill mentioned in his first lecture. The order of 1 terawatt is how much energy you radiate in these internal tides. You can do the same problem if you want to look at how much the balance part of the motion, the geostrophic flow, generate what are called Lee waves. Now it's a stationary problem, you just have a mean flow, again going over rough topography, and it radiates some stationary wave patterns. Again, also in that case, what you need to know is the velocity, the geostrophic velocity at the ocean bottom. This was estimated from a numerical model. Again, you need the stratification and you need topography. It turns out that stationary waves are generated at a much smaller scale than the tidal waves that care more about the slopes of the large scale features. So in that case, you use ship soundings. We don't have detailed maps of topography at small scales everywhere, but we can reconstruct it. So now we can compute also what is the generation of these, what are called Lee waves in the ocean interior, the generation of waves by geostrophic motions. And you see that the number is now 0.2 terawatts. Much smaller than the value here. The reason why it is important is that it's all confined to the Southern Ocean, where there is little generation of internal tidal waves. So you sum the two, and now you have the rate of generation in the wave field in the ocean. This part of the calculation, I think, is reasonably robust because it's a linear wave problem. It's now the next steps that become pretty hand-wavy. Now, this is the energy radiated in tides plus geostrophic motions. Now, the first step is just brute force. You say, well, what about 30% of that wave energy that is radiated into waves ends up going into wave breaking? The reason why you use 30% is that you know that places that are that generate only very large scale waves are not very good radiator of waves that tend to break locally where they are generated, just because long waves will propagate long distances. So in that case, you have places that will have only a small fraction, like 10% of the locally generated waves that generate mixing. The Hawaiian ridge, I think, is a good example of that. You have places like the Mid-Atlantic ridge which are much more efficient because instead they have more small-scale structure and they generate a lot of small-scale waves to start with. Those are more likely to break, and so the fraction is even larger than 30%. Geostrophic motions generate Lee waves and even smaller scale, so those are even more likely to break. So you take a value which is in between what is expected to be 30%, but that's mostly guesswork. And you'll see that that will affect the magnitude of the response, but it will not affect the qualitative pattern of what I'm describing. So now we know what epsilon is because we have Q times E is the energy flux that goes into breaking waves. And now we multiply by a function f of z, which is a function that tells us that the gravity wave breaking are more likely to break close to the ocean bottom and less farther up. This is based on the observational evidence, and when you look at this profile of turbulent diffusivity or buoyancy fluxes, they always have an e-folding scale with a decay scale of order 500 meter or so. Things tend to break quite a bit close to the topography. As you move further up, at some point the signal vanishes. So we're only capturing that part, and the function f of z is such that it integrates to 1, so that you're preserving the total energy flux. So now, once I know epsilon everywhere, I can use Osborn formula and I compute the buoyancy flux as a function of epsilon.
So, do you have a separate surface mix layer in addition to this?
We are not doing the budget for the surface mix layer because
you're right. You're at the Abyss. So
there I would be in serious trouble because I need to have the surface generation by winds and buoyancy fluxes, which are much larger than that. But
right. Okay, got it. Thank you.
No, thank you. Now you remember this formula. If I know W prime, B prime, and I can take its derivative, which are given mostly by my function f of z, which is a function of height above the bottom, then I should be able to compute how much upwelling there is, downwelling there is in the interior, how much upwelling there is in the boundary layer, regardless of everything else.
Yeah, one question. If you're using the Osborn relation, and you said that in the boundary you're going to be homogeneous, then you're not going to have any buoyancy flux.
Another very good question. So the hydrography I use, again, doesn't have any values in the boundary layer itself. But I'm fine because I want to compute the W prime, B prime all the way down to above the boundary layer. And then in what we do, brute force, we impose that the boundary layer, I think it's 100 meters thick here. And then we just say that the buoyancy flux goes to zero in whatever is the boundary layer, but you don't have any measurements down here. What matters is only how thick that boundary layer is, but the value up, what sets the transport is only the difference between here and there. So if I know the value at the top of the boundary layer, I already know everything I need to know. So here the big uncertainty is that I put the constant thickness of the boundary layer just because I don't know what it is. I use 100 meters because typically that's the closest value to the bottom topography I get from hydrography, so I cannot get any closer.
So when you use this value of 30%, so it means really the breakings that occurs almost instant, like very close after, short time after it's generated.
Yes.
But there might be some remote wave breaking on the continental shelf actually, or in that can be important. Like it can enhance.
Yeah. So now
mixing on.
Unfortunately, this thing goes on YouTube, so I get in trouble. But I think that my reaction to that has always been that when people go and measure turbulence close to regional topography where there is substantial wave generation because the topography is sufficiently irregular, they do find enhanced mixing rate. I don't know of any observation of a place in the ocean where there was no local generation and you get a burst of very strong mixing. It just doesn't happen. So the remote mixing probably goes but contributes to a background, and that background we know from direct observation is pretty small. So it might be coastal areas where there is already enough mixing because of other process, bottom friction and other things, that it doesn't contribute substantially. But I will contend that given present day information, the best assumption is that that background doesn't really do all that much because we don't see it particularly active somewhere where we notice a flux convergence of turbulence. But that said, yes, here I'm only looking at that small fraction that generate mixing locally where it is observed. In some sense, you know that the other 70% of the energy has to be still dissipated. It's not that it vanishes, but it doesn't get locally dissipated to where it's generated. But then quickly, so what happens if I do this calculation? Then this is the same calculation we've done before. Now I look at the flux of mass through a density surface in the full ocean, just of course not considering region of sinking, because we want to see what happens after the water has sunk. How does it come back? So the black line, so this is now neutral density surface. These are for the real ocean. So this is neutral density minus the compressive effects. This is the true thing because I'm doing it for the real ocean. And let's start. This is the largest values you get. Again, the black value is the total flux through that density surface, which is of the order, I don't know, 10 Sverdrup or so. At 28.1, we are somewhere down here in this plot. This is density and latitude. This is the total average overturning, and so indeed the value here is order of 10 Sverdrup. So these two numbers are consistent with each other. If I take the full flux across the density surface, it's like the flux across this density surface. So the two numbers are consistent. However, now I can split the transport between what happens in the boundary layer versus the interior. And you see in the boundary layer, you get close to 40 Sverdrups of water upwelling. And if I look in the interior, this is what, 30 Sverdrups of water sinking in the interior. So the overall budget here is that you have 40 minus 30 giving you 10. There is a lot of water rising along the boundary layer, and this time Jacques was asking if the slope of the topography is an issue. Now I'm really looking with realistic topographic features. I'm following the topography wherever it is, and it still seems to give you the same leading order pattern of a very strong cancellation between these two flows. So when I do a zonal average, I essentially average these two numbers, and I say, well, in the net, I just balance the 10 Sverdrup of water that is sinking around Antarctica and has to return back. But in practice, what is happening in the ocean pattern is that those 10 Sverdrup plus 30 Sverdrups that are sinking above topography in response to mixing generate 40 Sverdrup of water rising along the boundaries. And you should take all these numbers with grain of salt. I'm not trying to defend them, but the pattern is clear that there is a very strong cancellation. I think that's quite robust. How much time do we have left? Yeah.
We are flexible with time this morning.
Yeah. So what do we want to do next is that I hope at least I convince you a bit that this picture starts looking quite different from anything you heard from both Walter Munk and Henry Stommel. But you like to go back and understand a bit what is the pattern of circulation really develops. Here I've given you just most evidence for these upwelling and downwelling patterns, but as you can imagine, now I put lateral topography that apparently affect the stretching and squeezing of water columns. That's what Peter Reins told us already. And now I make it even more complicated because apparently upwelling and downwelling changes very close to the boundary. You remember that the stretching and squeezing was associated whether you had upwelling or downwelling. So that whole argument of how potential vorticity affect the circulation is not very clear anymore in this context. So we want to find what we think is the simplest dynamics that still captures this upwelling, downwelling along boundaries, but allows us to make some analytical progress and really understand the budgets of these boundary flows. As we heard, Bill was telling us that we can get solution for this boundary flow even for just constant molecular diffusion. We want to see how those solutions fit in the big picture. And then we want to see how these patterns of upwelling, downwelling modify the horizontal circulation, and are there predictions we can make about how that solution should come to be. And this is the system that we settled on. This is what are called the planetary geostrophic equations. So in the momentum equation, we ignore all nonlinear terms. We are thinking about the large-scale circulation, very small Rossby number, so we drop everything here. So this is just the Coriolis acceleration balancing pressure gradients in the horizontal, and we use some Rayleigh friction. We use Rayleigh friction because it makes the problem much simpler, and I will try to convince you that it does preserve the fundamental properties of these upwelling, downwelling patterns, which is the only place where friction really acts. This friction will be only important along boundary layers, not in the interior. That said, probably Bill is a bit shocked right now, because after what he told us yesterday, one thing that we know generally about turbulent momentum flux is that they should preserve momentum. Rayleigh friction doesn't. The reason why that is not terrible is, again, that frictional term will act only close to boundaries, where in that you do damn momentum, because eventually you have a boundary condition of, well, no slip or whatever you want. So momentum is lost there, and that is what this is really trying to represent. Then there is a vertical momentum equation, which is just hydrostatic balance. We have conservation of mass. This is the buoyancy budget, which is coupled to the momentum equation. And in the buoyancy budget, we could keep the full nonlinear terms. So planetary geostrophy keeps the full nonlinear dynamics in buoyancy, but linearizes the equation for momentum. Okay, so this is a much simpler problem than the full dynamics, but we'll contend that it captures everything we need. In particular, it allows us to link two literatures that have proceeded separately. There's been a lot of attempts to describe the ocean circulation in terms of planetary geostrophic dynamics, including the abyssal circulation. Most cases, actually, people don't keep this full equation. They replace this with some Wn square, some background stratification. They don't want to solve for the full nonlinear dynamics, but there have also been attempts to use the full nonlinear dynamics, but they consistently use vertical walls in their mind. So that is work is due to Joe Pedlowski, there's been Jochen Marotzke, and there have been a number of cases of people looking how mixing here might affect the solution of planetary geostrophy, but in configuration which don't allow for sloping boundaries. There is a whole separate literature, started with, I guess, with Phillips and Monk, as Phillips and Wunsch, Carl Wunsch, and then probably Chris Garrett is the person that contributed most to it, which is indeed studying this creeping flow along boundaries. In most cases, they were really thinking about molecular diffusion, which describes the dynamics that we are interested in. And in those cases, they were really interested only in the response of the flow along the boundaries and not how it connected with the global circulation. They use much more complex system to describe those dynamics. It turns out, however, the planetary geostrophy I'll show you captures that physics, so we know that this simple set of equations will be able to both capture the upwelling and downwelling solution along the boundaries, and then we know it's also used to describe the full large-scale circulation. So we should be able to put the two together and see how the overturning circulation and the zonal circulation are coupled together through this mixing. Oh yeah, I haven't. Oops, so if I go in the right direction, here they are. So, first of all, even before I describe the boundary condition, I had to tell you what domain I want to work on, and I'm going to work again on a bathtub. In this case, the bathtub has walls that are a bit steeper than the ones I had before, so we're trying to be a bit closer to maybe an ocean-like, but still, the aspect ratio, actually here, our slopes are too steep compared to the aspect ratio of the real ocean. I think we have a 0.1 slope versus a 0.3 slope. Sorry, we have a 10 to the minus 1 aspect ratio slope in this domain versus a 10 to the minus 2 to 10 to the minus 3 for the real ocean. And we can get into the detail of why we do that is to make the solution computationally more efficient. It doesn't change the qualitative aspect, but then yes, it changes the quantitative aspects. At the beginning, I'm going to show you, well, maybe let's describe first the boundary condition. We are going to prescribe the buoyancy 0 at the surface. The surface is equal 0. This surface should really be thought a bit like what was the density surface at 2000 meters that Paula was talking about. I'm looking at the circulation below the adiabatic circulation. So I'm just prescribing what that flat surface that Paula was drawing is like. We're going to have a no flux boundary condition through the boundaries. There is no flux through. You could put some geothermal heating. It's very weak. It doesn't drive much of a circulation. We just complicate the interpretation of the results. But you can put it. We have no normal flow boundary condition. Since we have Rayleigh friction, that's the only boundary condition we can use for velocity. We don't have an additional one. And then we're going to prescribe a profile of turbulent diffusivity, which is increasing towards the ocean bottom in a cell-similar fashion. So it's always equal to the value kappa naught at the ocean bottom and then decays exponentially from there up. And the first problem I want to do is one in which I prescribe a uniform stratification and I just let the system go. If I didn't have sloping walls but vertical walls, you have a lot of mathematicians here in the room. I assume that you all know how to solve the diffusion equation. It would be just a vertically stratified fluid with some vertical diffusivity. If you wait, you start eroding the stratification until the fluid is completely homogeneous and you would develop no flow. Right? So it's a bit of a boring problem. Turns out that it's not as boring, which comes back to Bill's point, if you have lateral walls, because even just prescribing a diffusivity, you're going to generate a flow. And that's why it's at least worth doing this exercise. So the first part of starting with initial stratification and seeing how the system evolves, it's useful because you have an intermediate non-trivial transient where you develop circulation and especially develop boundary layers, and that's what I want to show you so that then we can go back and do the full problem where we look at the first problem which reaches an equilibrium, but we'll know much more about the boundary layer structure that you get. So this is our domain. We start with a uniform stratification. Or maybe I should ask, now we have lateral boundaries. I start with a uniform stratification. Can you already guess what is the final solution of this problem, even though there are lateral boundaries? So I have a fluid which is stratified, and no, Paula is not allowed to answer. This answer, so it's a uniformly stratified ocean. It's in a finite geometry, but it could be your bathtub, and there is some mixing. It could be molecular, or it could be you stirring with a spoon. What do you think is the final state of that system? Uniform, right? So you know that eventually it goes always uniform with no flow. But before that happens, you get something like this. So this, you wait a fraction of a diffusive time scale, and I already start seeing, and for the moment I'm just showing you the solution, then we'll go and describe where it comes from. But I'm showing you a solution across a section here. This is in non-dimensional units between -1 and 1. The length of the domain is L. It's your full ocean. So I'm going to show you a section of the solution across at a latitude in the northern half of my hemisphere. Here I'm on a beta plane, so the parameter f is equal to beta y. This is my equator, northern hemisphere and southern hemisphere. And what you see, this is the vertical velocity across that section. Well, first of all, you see the stratification, right? I start with a uniform stratification, and the first thing that happens is see this isopycnon starts bending down because they have to satisfy the non-normal flow boundary conditions, so they bend. And in response, I start getting some red. There is an upwelling along the boundary and a downwelling above it, which at this point should start looking really boring because it keeps coming up. But that is telling me that this simplified problem is already having enough dynamics to capture that pattern. The second thing that I can show you is the meridional velocity, so the velocity into the page, into the section. And again, there is a red here, so the flow is coming in here and coming out here right along the boundary. So this is an anticyclonic circulation, and above it have flow red coming in and coming out, so there is a cyclonic circulation above it. So now I guess we pleased both Henry Stoneman and Peter Reitz, because we get both circulation, both cyclonic and anticyclonic. The problem is that you can decide that they're both 50% right or both 50% wrong, because both are there. It's not that it's obvious that there is a circulation one way or the other. So let's spend a second to understand the boundary layer solution itself. And this really goes back to, I think Phillips is the first paper that, together with Wunsch, they come out pretty much at the same time, which just solved for the solution along these boundary layer flows. The way they do it, if this is my sloping boundary layer, so this is the boundary and this is the normal to the boundary, they solve the problem in rotating the coordinate frame in the long slope boundary, and we're going to assume that the slope is uniform, right? We'll apply then this solution to also non-uniform slope by using WKB if we want. As long as the curvature of the slope is small enough, you can assume that it's constant. So now, the first thing you need to know, you had a stratified fluid to start with. That's the initial condition we started from. So I say that my B, okay, here I should have a B prime, is the background stratification plus a perturbation that develops in response of whatever dynamics is developing. But now the n squared was a vertical stratification. In this direction, I have to rotate B in the reference system of the tilted coordinates. So there is this theta. So this is along x, I have an n squared sine theta x prime stratification. So there is a stratification along the boundary. And then there is an n squared cos theta zeta prime. There is a stratification normal to the boundary. And then there is still the B prime, the perturbation. So this is the full stratification has this background plus B prime. Now, since I'm assuming in this problem, well, the first thing that I'm going to assume is that there are no variation into the page. The system is just two-dimensional. The second thing is that I also assume there are no variation along x because the stratification is uniform in that direction, so my equation don't have any explicit dependence on x. So I only have to worry about, if I don't have any dependence on x, it means that I don't really have any w velocity field. Wz has to be equal to 0 and w has to be 0 at the boundary. So I just have, for the buoyancy budget, B prime t, there is only advection along the boundary of the stratification along the boundary. And that is balanced by the vertical diffusion of the full stratification, which includes a background and it includes a perturbation. Remember that this is constant, but kt is z-dependent, so I have to keep it there. Okay? So now you start understanding that the budget here is quite different from the budget that Monk was talking about, because along this boundary layer, the balance must be between an along slope flow and diffusion of heat. It's not anymore between a vertical flow and diffusion of heat. And that's mostly because all these isopycna are impinging over that boundary. So now let's look at the solution itself so you can understand how that is going to work. The blue line is, let's say, that is the solution after some very short time when the isopycna started tilting down, and then over time they keep tilting more and more towards the boundary. Now you can try to understand what this balance really is, because what you see as the isopycnal tilt down, the water that was sitting here is getting progressively warmer, right? It was colder before, and then the isopycnal tilted down, so it's getting warmer. So this is a warming term. In order to achieve a steady state, what the system is doing is developing an upslope flow that brings cold water upward. So you have a balance between the upslope flow and the diffusion term. And once the two reach an equilibrium, this term can go to 0, and you have what is called an arrested Ekman layer. It's an arrested flow because now you have a balance between the upwelling and the diffusion. And this was indeed kappa T. Here it's a turbulent diffusivity, but as Bill pointed out, it could be a molecular diffusivity, you would still get the same response. Now you would have a creeping flow because the strength of the flow is proportional to the magnitude of kappa T, and turbulent diffusivity are pretty weak. As you know, if you ever try to wait for molecular diffusivity to mix your coffee and milk, it's actually a good exercise to do. I think Bill first asked me, you can try to do the calculation, then you do the calculation, go back to Bill all happy that you know how to compute the diffusive time scale, and he replies to you that it takes longer than it takes for the coffee to evaporate, so it never mixes. And that's the correct answer. But also here, indeed, molecular diffusion will give flows that are so weak that will have no relevance for the real ocean. But if this turbulent diffusivity is large, and we insist that it's large, then you get an upslope flow that is balancing this diffusive flux that is generated because of the boundary condition. Now, there is an additional twist to the story. You remember that we have a kappa T that is increasing towards the ocean bottom, and as a result, we said that our buoyancy flux is becoming larger and larger as I approach the boundary. So right above the boundary layer, where the isopycna has to tilt to match the boundary, you see that the red line is above the blue line. That's where you have the cooling. right? It's the divergence, it's the buoyancy flux is now convergent, so it's making the water cooling. And so you see the isopycna is moving up in response to that. I'm cooling it up. But now this balance still holds, so if this term is negative, I have to develop a negative U prime, and so there is sinking flow in response to that. And that's all captured by that simple dynamics. You can, well, if people are interested, we can actually look it afterwards. You can even write directly the momentum budget, and you find that U prime is really related to B prime in this system, and therefore, given the anomaly in B prime, you can infer which way the flow has to go, but the dynamics is pretty straightforward. And indeed, if I look at the simulation, and I look now, this is the upslope flow, and this is the flow along the slope. Forget about the blue line for the for this particular plot. You see the upslope flow right in the boundary layer, and then the sinking right above it. And the solution is smack on with the analytical solution, because you reach the steady state pretty quickly, and then it sits there for a long time. You could also compute the geostrophic flow along the boundary. Now you tilt the density surface, so you expect that there must be thermal wind and geostrophic flow in and out of the page. And if you spend the time, you'll find out that you get this cyclonic and anticyclonic circulation in response to isopycna that tilt up and down in the boundary layer and above the boundary layer. I guess the only thing that I want to add is that this whole solution works as long as you are along the sloping boundaries, because you need a sloping boundary to allow water to creep up and balance the diffusion in. If you are on the flat bottom boundary, you don't have this creeping flow or this diffusively driven flow along the boundary. So here instead you start destroying the stratification. So what happens in this solution, as you let it go, you develop very quickly the upwelling and the downwelling, and then you start getting a diffusive boundary layer that keeps growing here and destroying the progressively all the stratification over the flat area until the whole system is homogenized. So the solution eventually goes to the boring state you expect, but the boundary layer develops pretty quickly. So now we just looked at this as an oh yeah.
So it seems everything depends on using the diffusion equation all the way to the boundary. But is that a reasonable model even for molecular diffusion? I'm just thinking that the way Einstein derived the diffusion equation is by thinking of a random walk, and it relies on having steps which are symmetric, right? So you have no drift because there's as many steps down as there are steps up.
Yeah.
But near the boundary, this becomes wrong, right? So I'm just thinking,
so
can we believe diffusion all the way to the boundary?
I don't think it matters, because what really sets the circulation is the pattern up above the boundary. Then all that really matters is that there is a flux up here that goes to zero. And I know that the flux has to go to zero at the boundary itself. There cannot be a flux into the boundary, or if it is, it's very weak. The details of that shape are completely irrelevant at that point for the solution, meaning that the transport in that boundary layer is essentially set by the value of the flux up here. So I could have, if I use a different profile that does something more interesting, as long as it goes to zero, I will still get the same solution. Because the transport is set by that integral, not by the shape of the profile. So the value of kappa t shouldn't matter. So as long as that process that you're describing is conserving buoyancy, I don't think it would matter. If it doesn't, yes, it would matter. But I'd be surprised that whatever is mixing that buoyancy is not conserving the buoyancy itself.
Because I mean, there are people who start from kind of molecular dynamics and try to get the right behavior near the walls, right? And typically they find things which are not the equations that hold in the interior.
Yeah. My guess is that since the whole transport really depends on the value of double prime B prime there, I'm not so sure how much it would change the answer, but maybe it does, and it's worth thinking about it. I don't have an answer beyond that. Paola, maybe it does. There is another question.
Yeah, I'm wondering how much the results depend on the value of friction that you use.
Surprisingly little. Maybe we'll get to that in a bit. It turns out that if you change the friction, there are large compensations. I mean, the solution really doesn't depend on the friction itself very much. It depends on friction to the extent. What the friction really does is sets, we haven't described them yet, but there are additional boundary layers, the Mank boundary layers, the typical larger scale boundary layers that transport flow meridional, and it's the thickness of those boundary layers that changes, but not as much as the transport. If you wait a bit, we can get to that. It's a bit anticipating the answer.
So could you give us, so you show this cross section, but I'm having a hard time visualizing what the horizontal or elonga's apical circulation looks like, since you have both cyclonic and anticyclonic flow. So how does, going back to sort of stomal Aaron's gyres, how does it look like?
You cannot, because I'm not forcing it, but we're going to discuss them in detail when I put some force in, so I drive a circulation. Right now, these two circulations are just counter-rotating until they spin down, because they are not transporting anything.
So you have an external one that's going rotating in one way and
the other in the other way. And they just spin down frictionally at some point. Oh yeah, maybe the answer I've given, I was already thinking ahead when I said the friction doesn't matter too much. It doesn't matter too much for the steady solution I'm going to describe next. Here it would impact the spinning down time scale as well. But this is a pretty contrived exercise just to explain the property of this boundary layer and why we can actually solve analytically for them, and they show and they satisfy this simple analytical solution.
Can I ask you how it compares your boundary layer here where the flux changes? Well, it's not the boundary layer where the sign of the flux changes, and the curvature of the isopignals. I mean, you have a typical size.
So the isopignal have always to do something like this, right? So this is a straight line. My isopignal will always first bend up and then come down. And they do it if I prescribe a buoyancy flux that has a divergence and convergence no matter what.
Okay, and this size here in the normal to the slope, does it respond to this buoyancy flux that you impose?
Well, here I'm imposing a kappa T now, finally, right? I'm not imposing a buoyancy flux in the equation. This one of the main reasons to move beyond that state now is kappa T times a buoyancy gradient, so I'm not prescribing a flux anymore. Okay. But still, I'm going to get a flux divergence and convergence, mostly because kappa T is increasing towards the bottom, so for a while it's increasing fast enough that kappa T BZ is becoming larger and larger, but then I impose a no flux boundary condition, so it has to go to zero, so it reverses side.
It's increasing for the near the boundary, but there's a point in which it starts decreasing. So again,
so I can solve. So you can solve this boundary layer problem, and you can find the boundary layer thickness, which will depend on kappa T. If it is a constant, it's simple. It's just depend on kappa T, and depends on F, and depends on R, and all the opposed parameter.
It depends on kappa T where?
If it's uniform, it depends on kappa T. If I make it bottom intensified, it's a particular integral of kappa T, and it's not a trivial solution. You can solve it analytically, but it's a combination of Abyssal function. I didn't find anything particularly useful to help you guess what that boundary layer thickness is. It's some value above the bottom value.
Okay,
but it's a convolution that you have to solve for, which will be actually something very important. Maybe I can say it now. I was planning to say it later. I think that the issue why that is very important is that when you start talking about diffusive scaling for the global ocean, we'll understand that you can probably try this in some weak sense to defend some of these diffusive scaling arguments for the ocean overturning circulation, because we'll see that all this boundary flow set the stratification along the boundary, and then we'll discuss next how that circulation gets communicated to the interior. So in that sense, it's true. The problem you'll be stuck is that what is the appropriate value of kappa you can't infer, because you need to know exactly what is the solution in the boundary layer and what is the value of kappa that drives that upslope flow. So yes, after the fact, you can always find probably a kappa T that gives a solution which is not inconsistent, but you don't know until you solve the problem what that appropriate value is. But we'll find out as we solve the problem. Should we stop and resume, or do I keep going? Yes. Not too many more, but we can count. But it's 1, 2, 3, 4, 5, 6, 7, 8. About 8. And Bill has also to show something, right? So, well, 5 plus 6 is already